firstly, thank you very much for that very kind and generous introduction, and thank you for the welcome I've had all the time I've been in Malaysia. I've had a tremendous time the last 2 weeks. I've learnt an awful lot. I've been very impressed by everything I've seen at UMT, and I've really enjoyed myself, and the role I have means I come back several more times, so I shall look forward to that. So what I'm going to do today is to tell you a bit about what I've been doing in the North Sea, which is a cold, bleak place, a very long way from here. But at the end, I'm going to try and relate some of the ideas of what we've been doing there to sort of the things that might be done in this environment here in Malaysia. So what I'll do by way of an introduction is to tell you a little bit about why we should be concerned about the nutrients. And by the nutrients, I mean nitrogen, phosphorus, and silicon in these environments. Principally, those are the nutrients that stimulate algae to grow and cause eutrophication kind of problems if we have too much of them. Then I'm going to focus particularly on estuarine processes, on what happens as the rivers meet the sea and how important that is in terms of removing nutrients and changing the fluxes into coastal waters. Then I'm going to focus particularly on what happens as we change the shapes of estuaries. It's a particular interest of mine, how we've modified estuaries over centuries in the UK and we are doing worldwide, and how that's changing the behavior. And lastly, I want to come on to this idea of how some of the ideas that I've developed in the North Sea might play out in Malaysia. So this is the North Sea. I don't know if I can make which bit of this makes it go beep, but I'll just wander over here. The North Sea, I guess most of you know where Britain is at least, and it's the sea to the east of Britain. It's a cold, temperate sea with a very strong seasonal cycle. In winter, it's too dark and too cold for very much to happen. So as we go on, you'll see the impact of that seasonal cycle. And why are we interested in these processes? Well, in a way, this diagram sums up some of the changes we've been making. Oh, does it? Oh, brilliant. Excellent, excellent, thank you. This is an astonishing record that I came across a few years ago, because it's a record of nitrate concentration in the River Thames, which is the big river that flows through to London. But it goes back to 1870. I was just amazed to discover we have really quite reliable data going back that far. And what it shows you is the remorseless increase in nitrate concentration that's taken place in the river, with a distinct jump here and continuing at very high concentrations right through. To give you some context, as far as I can see from the data I've seen in Malaysia, your concentrations are somewhere way down here. So you've got much, much lower concentrations than these. But the reason why people are becoming very exercised about this is these concentrations are now approaching the limits for drinking water. At these concentrations, the water companies will no longer be allowed to use this water for public drinking supply. And that really focuses the mind on the requirement to try to control this nitrate. The story for phosphorus over time is a little different. That was for the Thames. All the rivers in northern Europe look very similar in terms of their history, but in the Rhine, the nitrate concentrations have increased similarly. Phosphorus increased and then has decreased since about 1980, and that's because we've taken out detergents primarily, or detergents that contain phosphorus. The story for silicon is really much more complicated, but largely silicon is not impacted by human activities, but it is decreasing because we're stimulating so much algal growth within the rivers. But the thing to remember is that the phytoplankton need all these three nutrients to grow properly. So this interaction between these changes is going to affect the coastal waters. And they are having effects. Here's just two examples of the kind of damage that can be done by this process. The first here is for the North Sea. And we have a traditional seasonal cycle over much of the North Sea, with the algae growing suddenly and rather explosively in about March, April, when the light begins to improve and the waters warm up. And over much of the North Sea, this is the traditional pattern. But if you come into the coastal waters near where the rivers go in, on the same scale, this is what you start to see. And the concentrations of algae are increased, the timing is changed, and the species are changed. And the net effect of that is that on the coast of Holland and Germany at various times, you have hundreds of meters wide foam all over the beach, resulting from the growth of these algae and the compounds that they emit. And clearly, when you have beach foams on this scale, then tourism is damaged and so on. The situation in the Gulf of Mexico is even more dramatic. There you have the Mississippi River draining into the Gulf of Mexico, bringing with it all of the fertilizer used in about half of the continental United States. That goes into the coast near New Orleans, stimulates algal blooms. Those sink to the bottom and consume oxygen. And you have what in typical American understatement is referred to as a dead zone that drifts all the way along the coast here for hundreds of kilometers. The bottom water in the summer season is devoid of oxygen. The fishery is wiped out. The livelihoods are wiped out. And this is a really dramatic example of what can happen if you put too much nutrient into coastal waters. Now, in the North Sea, I've always argued that we don't have such low oxygen environments. And that is broadly true, and the reason begins to emerge when you start constructing budgets for what goes on in these coastal waters. And this is our budget for the North Sea, and this is the river inputs, the atmospheric inputs, and the direct discharge. This table represents an enormous amount of work, but I won't bother you with that detail. But you can see we're putting in about 1.5 million tons of nitrogen extra each year. Now that sounds like a huge amount of extra nitrogen. But the interesting thing is the context, because you can also work out how much is coming in from offshore by exchange across the shelf here, and that's about 7.5 million tons. So yes, we've increased the nitrogen a lot. We've put in an extra 1.5 million, but it's against a background of about 7.5 million. So the system has been increased by human activity, but there's already a lot there, so it's probably not having a particularly drastic effect because there's naturally a lot of nutrient there. We're increasing it, we need to be concerned about that, but it probably hasn't reached a particularly damaging point yet. That said, over the last couple of years, we've begun to realize there are areas of low oxygen now developing in the North Sea. I'd highlight two areas here. One, is this focused, by the way? Is it clear to you all? It looks a bit fuzzy to me here. It's okay? Right. Two areas, one down here in the southern North Sea, where each year now we see a decrease in oxygen concentrations each summer season related to increased productivity. This is a large-scale map of oxygen in the bottom waters of the North Sea, and we can also identify a region here, quite a large region. The oxygen concentrations are not terribly low, but they're distinctly lower than around here at about 60%. You probably don't start to get biological effects until you drop to 30 or 40%. But this region, we have a data set here that allows us to go way back to about 1920, and you can see that this decrease appears to be quite a recent phenomenon in the last 10 or 20 years. We're not quite clear why that's occurring. We think it's a combination of changing physical structure and changing nutrient inputs. But this leads us to be interested in what's going on in coastal waters, and I have a general conceptual idea of coastal waters where rivers bring in nutrients. They go into very turbid waters. The dots are meant to represent the fact that estuaries are naturally very turbid places, and then they come out into coastal waters where there's much less turbidity, there's plenty of light, and the algae can start to grow. And to understand these, you've got to understand the inputs from the rivers, from the atmosphere and the groundwater, the interaction with the shelf and with sediments and with light on the outside. And what you find is that the pattern that develops in coastal waters is really complicated. This is an average of the chlorophyll in summer in the North Sea and the waters to the west of Britain. You see this really complicated pattern. This is chlorophyll, the indicator for the algae in the water. This complexity is a mixture of biological, physical, and chemical processes. But It means at any one time you've got a huge amount of variability going on. Each year there's a very strong seasonal cycle, as I mentioned. In winter in Britain it's too cold and dark for anything very much to happen. Come the summer, as in about the middle of April, we get a kind of explosive growth of algae called the spring bloom as the light climate improves and there's plenty of nutrient there and the algae grow. And in the process, they take out almost all of the nutrient that's been stored over winter. So you reach a stage very rapidly on a time scale of about 10 days. This system switches on and flips through this cycle. And you end up with very little nitrate in the waters. One of the things Sir Jaime Saratman did when he was with us was to work on the organic nutrients within this water, and his work and the subsequent work shows that when that nutrient disappears, the nitrate disappears, what actually happens is it turns into organic nutrient, which is then only very slowly degraded. And we're still trying to understand how these processes interact to produce the pattern that we see in the summer. So what I'm going to do now is focus on what happens to river inputs as they come into these waters, because that's the key determinant. Most of the nutrient is coming in, or most of the human-induced nutrients are coming in through the rivers. And there's 4 real processes that can operate. One is you can trap particles in estuaries. Secondly, you can have algal growth in estuaries. Then you can have bacterial processes, particularly denitrification, which I'll explain in a minute. And you can have interactions between the particles and the water. And I'm going to talk about principally 2 estuarine systems, both of them on the east coast of Britain. My own lab is based here in Norwich. The first is the Humber estuary, which drains through Hull and is the biggest river system in England. It's not quite the biggest in Britain. The Scots beat us for that. And I'm also going to talk about a much smaller one here called the Great Ouse, that drains in here into the Wash embayment down here, and the Great Ouse drains in through here. And I'm going to take you through what happens in the estuaries from this region, which is above the salt, but where the tidal reversal traps the water through the estuary itself and out towards the coastal seas. In the upper part of the estuaries, you traditionally have a piece of water that is fresh, but is still strongly influenced by the tides. So the water sloshes back and forth and doesn't go very far. The water is there for a long time, and time is key to almost all these estuarine processes. As the water sits there with all this nutrient in it, and plenty of light at this stage, you get enormous algal blooms. These are going up to 100 micrograms per litre. The waters I've seen down here are somewhere around about here. These are huge algal blooms, and with it, this is a map of or a time series of silicon, and you can see the silicon in the water disappearing as these blooms take place. So that silicon is not getting into the sea because it's being trapped by those algae right at the start of the estuarine process. Moving further into this more turbid waters where the tides start to stir up and the salt starts to play a role, we look at estuarine nutrients classically in an approach like this, where we plot the concentration of the nutrients against the salinity. And if you have conservative behavior where the nutrients are simply passing through the estuary without modification, you get a straight line. If you get curvature, it's representing some other processes going on within the estuary which are changing that flux. This is a really massive data set that we now have for the Humber, and that illustrates these kind of processes. You can see that for nitrate, it's essentially a straight line. It's conservative, it's not being modified in its flux as it passes through the estuary. And you can see for ammonia and phosphate, much more complicated patterns reflecting changes going on within the estuary which can act to trap those nutrients within the estuary. The last process I'll mention before I get on to some of the more interesting results is this idea of denitrification. It's a process that takes place in sediments, it's breaking down organic matter, and it's taking place where the oxygen has run out within the sediments. And what it does then is to use nitrate as an oxidizing agent convert that to nitrogen gas or sometimes N2O. So you're getting rid of nitrate by this process. And it's an extremely valuable environmental process that's acting to mediate much of the damage we're doing with nitrate. You can see some examples of those kind of processes at work now in the Great Ooze. Most of the estuary, the behavior looks conservative, but here you've got some curvature suggesting there's something going on, and the same down here, different seasons, and note also the big change in the concentration in the rivers, reflecting those algal blooms stripping out some of the nutrients. So to summarize what we've seen in those estuaries, basically you can remove phosphorus if it sticks to particles in the turbid waters, and that's a process that occurs quickly, timescales of minutes. Silicon you can only really remove biologically, and that requires algal growth, it requires light, and it takes days. Nitrogen is removed principally, I think, by denitrification, and that again requires sediment now for that process to take place, and again it takes days. So what we do is to create these nutrient budgets. And we do that if we know the concentration in the river and the flow into the river, we can work out the total amount of nitrogen going into the river. And then from these kind of estuarine studies, we can work out how much is removed. And we get to studies of how much nutrient is passing through the estuaries. And that's where I think it gets really interesting. The government were paying for this work because they want to know how much goes into the North Sea and how to manage that. And when we construct a budget now for the North Sea, we don't have very much good news for them. The nitrogen comes into the estuary and basically almost all of it, 90-odd%, passes straight out the other end. The estuary has no capacity to remove nitrate now at all. And so the monitoring that takes place here gives you the input to the ocean, and you've got all that nitrogen going into the North Sea with the threat that that brings of eutrophication. Now, this is where I think it gets exciting, and it's a slight diversion. But I think the first message from this is the value of doing really interdisciplinary work, because this now has a geological perspective for the next few minutes. I was working on the Humber doing this work about 10 years ago, and at the same time a very good friend of mine who's a geologist was also working in the Humber. But he was working on something completely different. He was reconstructing what the Humber looks like and how it has changed over the last 10,000 years. This may seem a long way away, but you'll see in a minute the link between that. The way they do that is to go through the Humber Basin, and this is a map of the Humber as it is now. And in all the intertidal areas and what is now dry land, they take sediment cores. They drill holes in the sediment. They work out how fast the sediment has accumulated over the past and what the concentrations of carbon and nutrient are. And in the process, they can recreate what the Humber looked like 3,000 years ago. And this is what it is. Due to human activity to reclaim the land in the Humber, 93% of this land has been reclaimed. It's massively changed the Humber. With that, you've lost the capacity to make any sedimentation in the estuary because it has all been turned into concrete walls. And with it, you've completely changed the light climate and the ability of the nutrients to sustain that nitrogen or to remove the nitrogen and so on, as you'll see. To explain what's been lost here, you'll be familiar with tropical environments. This is what a salt marsh, which is the main habitat that's been lost, looks like. It's a vast grassy meadow. At spring tide, this is completely covered with water. This is sort of intermediate situation. These can be kilometers wide. So they're very large habitats. And in your environments, they're replaced with mangroves in essentially the same setting. This is what we've turned that into now. This is part of the city of Hull, protected all the way along its boundaries by sea walls. Very expensive things, sea walls. They cost about £1 million for every kilometre of sea wall. So this is an expensive thing to create. Behind it, you've got, in this case, the city of Hull. You've got tiny remnants of the salt marsh remaining in parts of the Humber. So, as I say, all of that human activity, which as you'll see, has gone on in many, many estuaries, not just this one, completely changes the capacity of the estuary to deal with nutrients. So we set out to work out what the estuary looked like in a geochemical way 3,000 years ago. Now that, obviously, we don't have measurements from 3,000 years ago, but it's actually not as difficult as it first seems, because all of that geological work actually measured the burial of nitrogen in the Humber estuary 3,000 years ago. We can make an estimate of what the rivers were like 3,000 years ago because there was no intensive agriculture, and we compare to some suitably remote environment. In this case, I use northern Canada, which is broadly similar in terms of climate and is certainly very little impacted by human activity. So if you're burying 19,000 tons a year and you're only putting in 1 or 2 through the river, the only way you can make sense of this budget is if nitrogen 3,000 years ago wasn't exiting from the river and the estuary into the coastal waters, but was flowing in completely the opposite direction. The estuary 3,000 years ago was a sink for nitrogen, not a source to the North Sea. So if you put the two budgets side by side, you can see the dramatic changes we've made. The first, and the one you'd no doubt expect, is that we've increased the river inputs dramatically, probably 20 to 30 to 50-fold. So it's a really big impact of all that intensive agriculture. But furthermore, by all the changes we've made to the geography of the estuary, the reclamation we've done, we've actually changed its capacity to store nutrient. And 3,000 years ago, this was a store for nitrogen from the North Sea. The flow was in, now it's out. So it's not just that we've changed the amount of the flux, we've even changed the direction. We've done this, I argue, to almost every estuary in Northern Europe now. This is the Wash, this embayment I talked about further south from the Humber. There's the modern coastline. Here's our reconstructed coastline. For those of you who know Britain at all, King's Lynn is here, Cambridge is here. Cambridge would have been a seaside town, effectively, 3,000 years ago with all this. You see again this massive loss of habitat that's taken place, which of course has ecological impacts. And you see again that we're reconstructing a flux 3,000 years ago that was in exactly the opposite direction. So we're massively modifying these estuaries as a result of human impact. This has led me to try to think about a new way of assessing what goes on in estuaries by looking not just at the residence time of the estuary or what happens within it, but a ratio here between the area of the estuary and the flow into it. And this turns out to be incredibly variable between estuaries, between very low values and very high values. And these high values mean there's loads of estuary here in which to store the nutrients. And it's these estuaries that will be particularly effective stores. But the range of these values is almost a factor of 100. So what does this mean for the management of these estuaries? Well, in the UK, we face a number of challenges in terms of coastal management, some of which are similar to the ones you face here in Malaysia, and some of which are rather different. We have rising sea levels. I gather at the moment your sea levels are still falling as a result of changes since the Holocene, but I presume eventually sea level rise will overwhelm that. But we face rising sea level. We face enormous costs for sea defence. As I said earlier on, it's £1 million a kilometre to build those concrete walls, and they fall down after 50 years, so you've got to rebuild them. So it's a very, very expensive undertaking. So this means we've got to spend a lot of money on maintaining that infrastructure. In the case of places like the Humber, we've also got to maintain navigation. Those estuaries are important ports for us. So those are the sort of societal requirements, but we also have recreational demand. People want to use those wetlands for all sorts of reasons, for looking at birds, for walking. They're very important recreational environments. We also have European legislation that protects wetlands. And you have similar legislation, I think, protecting your wetlands, obviously not European legislation. So these are valuable habitats that we have to protect. We also have European commitments to nutrient reduction. the ministers all locked themselves away one weekend and all signed up to reduce nutrients by 50% without actually having the faintest idea how they were going to do it. And we have singularly failed to get anywhere close to that. And all of this is taking place in the face of climate change that's going to increase all sorts of other pressures in the environment. So what we've been doing is to think about the economics of this process. So I've now traveled a long way from a degree in chemistry to working with economists. It's an interesting challenge. I didn't even understand most of the words they were using. But within the Humber, we can identify a number of areas where these sea defences do not protect particularly valuable infrastructure. Clearly, we can't move to damage cities and so on, but much of this sea defence is actually protecting rather low-grade agricultural land. So we've started to talk in Britain about something called managed realignment, where we will abandon sea defences and we will start to move them back, give back the land to the sea, which is going to happen inevitably as sea level rises, but to do it in a managed way, and then to recreate the salt marsh habitat behind it, to give back the capacity for wildlife to live in there and also for nutrient storage. So what we've been doing is identifying within the Humber where those areas are, and we can then go through a really quite complicated economic calculation here of the costs and the benefits of that. What does it cost to do that in terms of land costs? We lose farmland. We don't lose much, and it's poor grade farmland. We have to build some new structures, but we don't have to rebuild the full sea defences. And then we can try to evaluate the benefits. Some of them are relatively easy to cost. Actually, the carbon storage benefit we can actually cost in terms of money relatively easily. Costing the nutrient retention is more complicated. The ecological value and the recreational value are really quite complicated to calculate. But at the end of the day, you can. I'm sure you can't read this table. I don't intend you to read this table. But just to show you the kind of complexity you go through, we do have in here the value of the carbon storage, the value of the nutrient storage, the value of the recreation. And at the end of it, you can present planners with costs and benefits. If you look over 25 years, it is not worth getting rid of the sea defences. The costs and the loss of habitat and so on, loss of farmland, means it's not an economic asset. But as you go further out, interestingly, the ecological benefits accrue over time. The cost of maintaining the sea defences keep going up. So if you look over a 100-year time scale, you are better to abandon these sea defences in an economic case than to retain them. So it's an interesting exercise in how long into the future you plan. When we started this, the government liked to plan in 20-year cycles. They're beginning to understand these points and start to plan in 50-year cycles, which is the lifetime of these sea defences. So we're beginning to engender some sort of change in the thinking there. So just to finish now, I want to mention how some of this might apply here in Malaysia. You don't have salt marshes, you have mangroves, but the same idea of the value of the mangroves as habitat and as storage of carbon and nutrients should be there. And it should be possible to start engaging in this kind of broader debate. It's called blue carbon in some circles, about the value of these salt marshes and mangroves in this case for all sorts of societal purposes. And it helps to quantify the value of conserving these habitats. I notice also in Malaysia you have the same engineering changes going on within the coastal environment. This is more or less the view from my hotel window. And Terengganu, which would have obviously hundreds of years ago been a natural estuary, is now embanked. And the changes you've made recently to create the large breakwaters at the seaward end seem to have changed the estuary quite substantially, and very little salt water now comes in. So the whole system, as with our estuaries over the last few hundred years, is now changing here. The other thing that I'm really looking forward to interacting with is your new programs in the South China Sea. You have this wonderful new research vessel that I was out on Monday, and you have a program working through these environments, and I'm really interested to see how your nutrient inputs affect your coastal zones. Your nutrient inputs are much, much lower, So I think you're going to see some very different patterns to the ones that we see in the North Sea. So I'm looking forward to the next few years of coming here. And if I can just finish by thanking you for your attention, but above all for the welcome I've had over the last 2 weeks. Thank you very much indeed.
My name is Paul from Department of Chemical Science. I have one question. You show a conceptual diagram showing the coastal nutrient cycling. And you're showing there's a groundwater input into the estuary. Can you explain more about the role of groundwater?
Yep.
Yeah, related to the nutrients cycling in estuary environment. Thank you, Prof.
Sure, thank you. Groundwater is an interesting issue. It potentially goes into both estuaries and further out into the coastal sea itself in some environments. The impression I have is that in many systems, groundwater is a minor source compared to the river. But then there are a group of environments where it becomes very important. You can have limestone coastal environments, of which the Adriatic coast in the Mediterranean would be an example, where essentially all the flow goes through the groundwater. And I used to work in Bermuda, and that's an example of a tropical island, a tropical limestone island, where we had no rivers at all. And again, all the freshwater nutrients came in through the groundwater. So I think groundwater's a minor player in many river systems and many ecosystems, and in a few, it is absolutely the most important one. And I think these, certainly in terms of things like tropical islands, it becomes a really important issue to manage. And of course, the thing about groundwater is it exchanges and flushes much more slowly than a river system will. So once a groundwater is contaminated with nitrate, it'll be contaminated for decades. Whereas in a river system, if you were to change agricultural practice in the catchment overnight, which is unrealistic, I know, but you would have a much quicker response within the river. So I think groundwater is a very important player. It's also important in the river system as well. That interesting hiccup in the Thames nitrate in the 1950s is beginning to be seepage of nitrate through groundwater, apparently.
About inputs of materials into the sea. I wonder what your thoughts are about, let's say, large-scale oceanography of the South China Sea versus coastal work and the interrelationships and so on. What do you think should be our focus over the next years or so?
That's an interesting question, and how large is large scale would follow from that, and you could have that debate for a long time. I'm still very much learning about this environment, but from what I understand, the shallow water shelf extends sort of way out here. So you're dealing with one of the largest shelves in the world. Beyond here is deep oceanography, and I could see no direct connection and no sense in a large-scale Malaysian-led program going out there. I'm sure as you develop, you will partner with some of the larger countries, probably one of the particularly large countries to the north that has a deep-sea oceanography fleet, and maybe want to work in this environment. But I think this shelf is very large, it's very important, and I think that's the logical place to focus. Now, one of the things, this is a satellite chlorophyll map, and I was seeing some very nice physical oceanography from this region from your colleagues here. This is a really complicated region in terms of the circulation, the monsoonal reversal of that circulation. You have some large rivers coming in here and here that are going to come down onto this coast. So I think there's a wealth of really interesting science to be done, presumably on both coasts. I've only thought about the eastern coast so far. This looks like a pretty complicated environment with a long, narrow flume. But I think you've got a wealth of really interesting stuff here. Now, how far out you go, I think, is an interesting question. One of the questions that will apply is do you have the situation we have in the North Sea where much of the nutrient is coming in from these offshore environments, in which case you're going to need to know something a reasonably long way out in order to understand how that's impacting the waters. I simply don't think we really know. There's some really interesting sort of jets running through this region, but I don't think we know where most of the nutrient is coming from at the moment. And your river concentrations look so low that I'm sure your shelf is still currently dominated by the natural cycle, wherever that nutrient's coming from.